Welcome to this explainer. Today, we're diving into a massive biological mystery. Why, despite decades of intense global effort, does a definitive cure for cancer still completely elude us? I mean, we hear about major breakthroughs almost constantly, right? But the actual reality on the ground is just incredibly complex. Let's get into it.
Think about this huge contradiction for a second. Globally, we spend hundreds of billions of dollars, yet the word cure almost never shows up without a giant asterisk attached. So what's going on? Was the science just wrong? Did we somehow not spend enough money? Or are we dealing with a fundamentally different kind of problem here?
Here's our roadmap for untangling all this. We're going to cover the 50-year war, the ultimate identity crisis, evolution inside your body, metastasis and hidden dormancy, the economics and lab gaps, and finally, winning 200 wars. Basically, we need to completely shift our perspective from seeing cancer as a foreign invader to understanding it as an internal evolutionary process.
Section 1. The 50-Year War and the Unfulfilled Promise of 1971. Let's jump right into the historical event that really set up our modern expectations.
Way back in 1971, the U.S. National Cancer Act was signed, and the logic at the time was, hey, let's treat this exactly like the moon landing. People really thought if we just threw enough money, enough brilliant scientists, and enough sheer national willpower at the problem, the disease would just surrender. But look at the stark contrast here. We assumed brute force would work, yet today, 50 years later, cancer is still the second leading cause of death worldwide. It kills roughly 10 million people every single year, and honestly, it's definitely not a resource problem, especially since the global treatment industry is pulling in hundreds of billions annually. So what are we missing?
That brings us to Section 2, the ultimate identity crisis and the targeting problem. To figure out why endless resources haven't fixed this, we've got to look at the crazy identity crisis happening right inside ourselves.
Think about when you get a bacterial infection. That bacteria is a totally foreign object. It has a clear boundary, it has foreign proteins, and the line between what is you and what is not you is crystal clear. That makes the target really identifiable. But cancer completely collapses that boundary, because cancer is literally made of you. It shares the exact same biochemistry and the exact same structures as the perfectly healthy tissue you're trying to protect. And honestly, this is exactly why chemotherapy, which has been our go-to treatment for decades, works the way it does and why it fails the way it does. It just blindly attacks rapidly dividing cells. It doesn't know the difference between a rogue cancer cell and your hair follicles or your bone marrow or your gut lining. It just hits them all.
So the massive takeaway here is that killing the cancer without killing the host is categorically one of the hardest targeting problems in the entire history of medicine. You are literally fighting a version of yourself that just decided to stop following the rules. Moving on to Section 3, evolution inside your body and a microscopic ecosystem. Let's zoom into the cellular level to see how this becomes an absolute evolutionary battleground. Okay, so your body contains roughly 37 trillion cells. That's a mind-boggling number. And every single time one of those cells divides, it has to accurately copy a complete genome made up of about 3 billion base pairs of DNA. But here's the catch. The copying process isn't perfect. Every single division introduces between 1 to 10 totally random mutations. Now, multiply that tiny error rate by trillions of cell divisions over the entire course of your lifetime, and yeah, the math starts to look pretty intimidating, right? But thankfully, your body comes equipped with these incredibly robust, multi-layered defenses. You've got tumor suppressor genes that act like biological brakes, proofreading mechanisms that constantly scan for and catch those copying errors, and apoptosis, which is basically just a fancy term for programmed cell death when a cell knows it's too damaged to go on. Plus, you have an immune system constantly on patrol. Cancer actually only takes hold when a single cell accumulates hundreds of specific mutations over decades, causing enough of these fail-safes to break down all at the exact same time. And this leads to arguably the most crucial conceptual shift in biology over the last 20 years. We realized a tumor isn't just some uniform lump, it's a living ecosystem of competing cell populations. So what happens when you hit a tumor with a cancer drug? Well, you kill off the most vulnerable cells. But some of those cells, just by total random mutation, are naturally a little bit resistant. They survive the drug, they reproduce, and the tumor that eventually grows back is entirely descended from those hardened, resilient survivors. Without meaning to, we're actually running a selection process that breeds drug-resistant cancer.
Section 4. Metastasis and hidden dormancy. These are our complexity multipliers. Let's confront the things that actually make this condition so incredibly lethal.
First things first, we really have to stop talking about cancer like it's a monolith. It's not just one disease,
We're actually dealing with over 200 distinct diseases. They completely differ in where they start, their genetics, how they grow, and how they react to treatments. Pretending lung cancer, leukemia, and melanoma are just variations of the same thing is honestly like treating pneumonia, tuberculosis, and asthma as the exact same problem just because they all happen to be in your lungs. It just doesn't work that way.
And then consider the incredibly grueling biological obstacle course a cancer cell has to survive to actually metastasize, which, by the way, is when the disease truly becomes deadly. A single cell has to detach from the main tumor, survive the wildly hostile environment of your bloodstream, completely evade your immune system, force its way into a brand new, distant organ, and then figure out how to reactivate its growth there. If a patient has cancer that has spread to their liver, lungs, and bone, they basically have 3 entirely separate tumors to treat, and get this, each one might have a totally different genetic profile. Add to that the absolute nightmare of tumor dormancy, where cancer cells can just go to sleep, completely invisible to treatments and our best imaging tech, only to wake back up years or even decades later. It's wild.
Section 5. The Economics and Lab Gaps. This is all about why mice lie and why development costs soar. Moving beyond just the cellular biology, we need to look at the real-world systemic hurdles that explain why so many lab breakthroughs fail to help actual humans. We've all seen those flashy headlines about some new miracle cure working in a lab only for it to completely flop during human trials. Well, the hard truth is, mice lie. A mouse bred in a lab is genetically uniform. It lives in perfectly controlled conditions, and it often has an artificially weakened immune system. Real human patients? We are incredibly genetically diverse. We have decades of messy biological history, and our immune systems are unimaginably complex. So the main takeaway here is that a lab mouse represents a fundamentally simpler biological system. That makes those exciting lab headlines systematically misleading when it comes to predicting what will actually happen in a complex, messy human clinical trial.
We also can't ignore the economics of the situation. It costs an estimated $2 to $3 billion with a B to develop a single new cancer drug. That is a massive investment, and it requires a return. Unfortunately, this creates a huge structural bias. It pushes the industry toward developing treatments that can be sold repeatedly to a patient rather than focusing on prevention methods which are notoriously difficult to monetize. Think about it. Proving a drug extended a patient's life by 6 months is totally measurable, but proving a drug actually prevented a recurrence, you'd have to track patients for decades just to prove that something didn't happen.
But hey, despite all those totally daunting systemic hurdles, there is a ton of incredible hope right now, especially in early detection. Technologies like liquid biopsies are advancing at a breakneck pace. These are simple blood tests that can detect tiny fragments of cancer DNA shed by tumors directly into the bloodstream, long before a patient feels any symptoms. And catching a tumor early, that completely flips the odds in our favor. For instance, stage 1 breast cancer has a 5-year survival rate of well over 90%, but at stage 4, that drops below 30%. The biology of the cancer is exactly the same. The only difference is time. Finding it early makes the treatments we already have infinitely more effective.
Section 6. Winning 200 Wars and the Path Forward. Now that we truly understand the monumental obstacles we're up against, let's talk about the genuine, absolutely incredible victories happening in medicine right now.
The successes we're seeing recently are just profound. Take childhood leukemia. It used to be almost universally fatal, but today, it's curable in roughly 90% of cases. Hodgkin lymphoma has been completely transformed into a highly treatable disease. And let's talk about immunotherapy. We now have checkpoint inhibitors that literally reach in and remove the molecular brakes that tumors put on a patient's immune system. This is creating long-term remissions for people with advanced melanoma who literally had 0 options just a few years ago. We even have CAR T-cell therapy. This is where doctors physically take out a patient's own immune cells, functionally engineer them in a lab to be specialized cancer hunters, and then put them back in to aggressively hunt down resistant blood cancers. It is straight out of science fiction.
So, let's look at the future and see how all this builds into the next decade of oncology. We are fully entering the era of truly personalized medicine. Artificial intelligence is stepping in to rapidly crunch the mutational profiles of tens of thousands of tumors, handling a scale of data that no human brain could ever process on its own. We're also seeing mRNA technology, which you probably know from recent vaccines, being deployed to create personalized cancer vaccines. These are explicitly tailored from the ground up to target the unique genetic signature of one single patient's tumor. Add those multi-cancer early detection blood tests into the mix,
And the landscape we're looking at today is worlds apart from where we were in 1971.
You know, there's a fantastic saying that in medicine, learning and winning are eventually the exact same thing. The incredible researchers fighting this battle day in, day out, they are not losing, they are learning. Every single time a drug fails or every time a tumor develops a new resistance, it teaches us something new about the deeply intricate, hidden mechanisms of our own biology.
Look, we are never going to defeat cancer with a single sweeping magic cure. The fundamental biology of our bodies makes that completely impossible. But instead, we will control it. We'll do it disease by disease, subtype by subtype. So as we continue to untangle this wild, microscopic ecosystem and start winning these battles one by one, I want to leave you with this thought. Knowing that we are actively fighting 200 distinct evolutionary wars simultaneously, which one will our rapidly advancing science win next?